Hi students, today we are going to derive an expression for the magnetic field due to a toroid. First of all, let us understand what is a toroid coil. So first we will consider this is a solenoidal coil carrying current of I ampere. A long solenoid is bent in the form of a circular loop, that is in the second picture. The solenoid is bent in the form of a circular loop whose shape is donut shape, having space at the center. Such a coil only is called as a toroid. And you have to notice that the current I ampere enters through the loop and it passes through each circular loop and comes out in this direction. So in each circular loop, the current is entering inward and coming outward. Now, I have considered 3 points on this toroid. One is point P. So, this point P is at a distance R1 from the center O. So, this point P lies inside. This is called as interior space. Interior space of the toroid. And can you see another point Q here? It is outside the coil. So this point Q is lying at a distance R3 from the center, where it is lying in the exterior space. So P lies in the interior space and Q lies in the exterior space of the toroid. And we are going to prove that at P and Q, that is in the interior space and exterior space, there is no magnetic field due to the current in the toroid. We are going to prove that. One more point, S, can you see here? Yes, this point S is along the axis of the coil. That is inside the coil, okay, inside the toroid. And it is at a distance of R2 from the center O. So only at the point S there will be a magnetic field. That is what we are going to prove. So what is the expression for the magnetic field due to the toroid we want to derive? Now a schematic diagram of this coil I have shown in the third picture. So can you see here this orange line and this orange line? These two circles are only the actual coil. This is the actual toroidal coil. So here the wire is going inward. Here at these X marks, the current also is going in the inward direction into the board. And it is coming through these circles outward. So I have written here current outward at these marks, these 0 marks, circle marks now. At all these points, current I is coming outward, and all these X marks, the current is flowing inward. So this is the actual coil. Now I have taken the point P in the interior space of the coil and Q in the exterior space of the coil and S between these two, that is inside the coil. This is in the inside of the coil. So these points are P, Q and S I have taken. Okay. Now we want to derive this expression for magnetic field using Ampere's circuital law. We have studied Ampere's circuital law. I am going to apply the Ampere's circuital law for these 3 points P, Q and S. So now first I will take the point P at P. Where is the point P now? Look at the point P here. Where is the point P located? It is in the interior space. So this is in the interior space of the solenoid. At what distance it is located is R1 from the center O. So I have to construct an Amperean loop passing through the point P. Amperean loop passing through the point P. Understand? And the circumference of this loop, the circumference of this Amperean loop, L1, say for example it is L1. this must be equal to 2 pi into R1. This is the total length of the Amperean loop. Now at this point P, applying Ampere circuit law, this is closed integral. So this is the first loop 1 passing through the point P. So for this loop 1 passing through the point P in the interior space, I want to find B dot dl. Understand that? And this is the magnetic field at the point P. So a suffix P I have taken. So Bp dot dl must be equal to mu naught times the current I enclosed by this Amperean loop. Understand that? Okay. Now you look at the point P once again, and the dotted line circle. Now this is the Amperean loop. You can see that the current flows inward here at these X marks, but these X marks are not lying inside the Amperean loop, they are lying outside. So there is no current flowing inside this Amperean loop. No current is flowing either inward or outward. So I enclosed is equal to 0. Understand that? I enclosed is equal to 0, and therefore integral Bp dot dl is equal to 0, and Bp into dl, okay, dl into cos 0 is equal to 0. This is a line integral. So now this is Bp. At all points on this circle, the value of Bp must be same. So I have taken out of the integral, and this closed integral dl is equal to 0, or Bp into integral of dl will be equal to the loop length L1. So this is 2 pi R1 is equal to 0. Therefore Bp is equal to 0. So there is no magnetic field at this point P. Have you all understood first of all? So point P is taken inside the interior space where there is no current flow. So the Amperean loop passing through the point P does not enclose any current. So the right hand side is equal to 0. Here itself we can close the derivation. Anyhow, we are extending this up to the last step, and we have proved that at point P the magnetic field is equal to 0. Okay. Now let us take another point in the exterior space. So I will take at point Q. So at Q, this is in the exterior space. We can see that Q is lying at what distance? R3 in the exterior space. So now I have to imagine a Amperean loop passing through the point Q. So can you see this dotted circle which is passing through Q? Okay. And all these diagram representation, everything is included because it's a larger circle, is it not? So in this Amperean loop also, you can see that current is flowing in the inward direction through the X marks, and the current is coming out through the circle marks outward. So the current flowing inward and the current flowing outward will cancel each other. They will cancel each other, and hence in this Amperean loop also the current enclosed must be equal to what? 0. So I will write here I in is equal to I out. If you add all the currents flowing through the inward direction, and it will be equal to the current flowing in the outward direction, and hence I enclosed is equal to 0. Understand that? So if you go by these steps, so Amperean loop length L2 I will take this is I mean L3 I will take because the radius is R3. So I can take this loop as a L3. So this is equal to what? 2 pi into R3 and closed integral for loop 3. This is a loop 3 because it is R3 I have taken. So into B Q dot dl is equal to mu 0 into I enclosed. So I enclosed here also what? I enclosed is equal to 0. Okay. And integral of BQ dot dl is equal to 0. And therefore here also what? B at Q is equal to 0. I can complete here itself. I need not extend up to all the steps because it is very clearly understood that the right hand side I enclosed is equal to 0. Therefore, B dot dl is equal to 0. Therefore, at Q, the magnetic field must be equal to 0. And now, we take one more point, S, inside the coil itself. Okay, children? So, I will take here at point S. So, this is inside the coil. So, we have to assume a circle, dotted circle, which is called the Amperian loop passing through the point S. So, S is at a distance R2 from the center O. So, the radius of this green circular loop is R2. Okay. So, the length of the Amperian loop L2 is equal to 2 pi into R2. Okay. And now what is the Ampere circuit law here? We will write Ampere's circuit law for this loop 2. This is B dot dl is equal to mu naught into I enclosed. Okay. Now you see here this is closed integral B S, okay, at point S into dl into cos 0 is equal to mu 0 into current enclosed. Now you see the green circle which is passing through the point S. It includes only the currents entering through these X marks, and it does not include the current which is flowing outward through the circular marks. And hence, what will be the net current flowing through these X marks only will be included. So, this is equal to I inward only. Only the current which is flowing in the inward direction is included. Are you understanding this? Because the current which is coming out of the toroid is coming out of the Amperian loop, which we cannot consider. So, I enclosed must be equal to all the sum of all the currents flowing in inward direction only. Understand that? Okay. So, this is now equal to Bs into integral of dl, and this is equal to mu 0. Now, how much current is flowing? Can you see here in every loop current is flowing inward here, okay? Suppose if there are total n number of loops, okay, then the net current, inward current must be n times I. Understood that? Now Bs into integral of dl must be equal to the length of the Amperian loop, that is equal to L2. So Bs into L2 must be equal to mu naught into n into I, where capital N is the total number of loops. So now Bs must be equal to mu naught into n divided by length L2 into I. Now the total number of lengths divided, total number of loops divided by the length of the loop must be equal to small n. So n divided by L must be equal to small n. Therefore, what is Bs is equal to mu naught into n into I. Okay, so this is the expression for the magnetic field at the point S, which is in the inside of the coil. Understand? So, you must know, my dear students, there is no magnetic field at any point in the interior space as well as the exterior space of a toroid. There can be only a magnetic field which is at any point in the inside of the coil. Understand? And you can see that this is the same expression as that of the magnetic field due to a solenoid. But for a solenoid, one end will be north pole, means other end will be south pole, like this. So the two polarities will be there for the solenoid. Whereas there are no poles, there are no magnetic poles for a toroid. This is a very important point. For a toroid, there are no magnetic poles, but there will be a closed magnetic field inside the donut shaped coil, and it will be a continuous circular path. Understand? But there will be no magnetic poles like that of a bar magnet or a solenoidal coil, and there is no magnetic moment also for this toroid coil. Only there will be a magnetic field. Understand? And its expression is what? Mu naught n into I. I hope you must have understood well. Fine.